Mercury, the forgotten planet that breaks all the rules. Part 1. Mercury's tiny size and giant iron core. Mercury, the smallest planet in our solar system, presents a fascinating paradox with its diminutive stature yet remarkably dense composition. Its diameter is only about 4,879 kilometers, making it just slightly larger than Earth's moon. Despite this modest size, it possesses an extraordinary average density, second only to Earth. This high density provides a crucial clue about its internal structure, suggesting something truly unique lies beneath its heavily cratered surface. Scientists have long been intrigued by this cosmic anomaly, as it challenges conventional understanding of planetary formation and evolution. The prevailing scientific explanation for Mercury's exceptional density points to the existence of a colossal iron core. This metallic heart is believed to constitute an astonishing 60 to 70% of the planet's total mass and volume, a proportion significantly higher than any other terrestrial planet. For comparison, Earth's iron core makes up only about 15% of its volume. This massive core effectively makes Mercury a giant metallic ball, thinly veiled by a rocky mantle and crust, a configuration that has profound implications for its magnetic field and thermal history. The presence of such an enormous iron core suggests a violent and transformative past for Mercury. One leading hypothesis proposes that early in its history, Mercury may have been a much larger planet, perhaps twice its current size. A catastrophic collision with another substantial protoplanet could have stripped away most of its lighter silicate mantle, leaving behind the dense iron-rich remnant we observe today. This giant impact theory, while still under investigation, helps explain the disproportionate core-to-mantle ratio and the planet's overall composition. Another theory posits that the Sun's powerful gravitational forces and intense heat during the early solar system played a significant role in shaping Mercury's composition. As the protoplanetary disk formed, lighter elements and silicates might have been preferentially vaporized or pushed away from the inner regions, allowing heavier iron to condense and accumulate more readily close to the Sun. This process would have naturally led to a planet with a higher metallic content, though perhaps not as extreme as what the giant impact theory suggests. Understanding the origin and evolution of Mercury's massive core is critical for unraveling the mysteries of the inner solar system. The extreme conditions near the Sun would have influenced the accretion of material and the subsequent differentiation of the planet into its distinct layers. Studying Mercury provides a natural laboratory for examining how planets form and evolve under conditions vastly different from those experienced by Earth or Mars, making it a key target for planetary scientists seeking to refine their models of planetary genesis. The internal structure of Mercury, dominated by its iron core, also has a direct bearing on its surprisingly weak global magnetic field. Unlike the Moon, Mercury does possess a magnetic field, albeit one that is about 100 times weaker than Earth's. This magnetic field is generated by a process called a dynamo, which requires the convection of molten iron within the planet's core. The persistence of this dynamo, despite Mercury's small size and rapid cooling, indicates that at least a portion of its massive core remains liquid, a testament to its unique thermal properties and internal dynamics. The composition of Mercury's core is not entirely pure iron. It is believed to be an iron-sulfur alloy, possibly with other lighter elements. The presence of sulfur would lower the melting point of iron, allowing a liquid outer core to persist for longer, thereby sustaining the dynamo. Seismic data and gravitational measurements from missions like MESSENGER have helped scientists infer the approximate size and state of the core, confirming the presence of both a liquid outer core and a solid inner core, much like Earth's, but on a proportionally grander scale. The massive iron core also significantly influences Mercury's gravitational field, which impacts the trajectories of spacecraft orbiting the planet. Precise tracking of these missions allows scientists to map variations in Mercury's gravity, providing further insights into the distribution of mass within the planet. These gravitational anomalies can reveal details about the thickness of its crust, the density of its mantle, and the precise dimensions of its colossal core, painting a more complete picture of its internal architecture. In essence, Mercury's tiny size belies its profound internal complexity, driven by its giant iron core. This core is not merely a passive component, but an active participant in the planet's geological and magnetic processes, influencing everything from its surface features to its interaction with the solar wind. Studying this unique core provides invaluable data for understanding the fundamental principles governing the formation and evolution of rocky planets, particularly those in the harsh environment of the inner solar system, making Mercury an indispensable object of scientific inquiry. The unusual characteristics of Mercury's core also pose challenges for planetary formation models. While the giant impact theory offers a compelling narrative, the exact mechanism for removing such a large fraction of the mantle remains a subject of active research and debate. Refining these models requires not only observational data from space missions, but also sophisticated computer simulations that can reproduce the extreme physical conditions of the early solar system and the energetic events that might have shaped planets like Mercury into their current forms. Ultimately, Mercury's giant iron core serves as a cosmic fingerprint, a unique signature of its violent and transformative past. Its disproportionate size and composition continue to push the boundaries of our scientific understanding, urging us to reconsider the diverse pathways of planetary development. As we gather more data from ongoing and future missions, the mysteries held within Mercury's metallic heart will undoubtedly yield further revelations about the dynamic processes that forged our solar system. Part 2. A planet closest to the Sun but freezing at night. Mercury holds the distinction of being the closest planet to the Sun, orbiting at an average distance of about 58 million kilometers. This proximity subjects it to intense solar radiation, resulting in scorching daytime temperatures that can soar to an astonishing 430 degrees Celsius. At such extreme temperatures, lead would melt on its surface, illustrating the incredible heat absorbed by the planet during its long day. This blazing inferno might lead one to assume a uniformly hot environment, yet Mercury harbors a surprising secret: nights that plunge into unimaginable cold. Despite its scorching days, Mercury experiences dramatic temperature swings, with nighttime temperatures plummeting to a frigid -180 degrees Celsius. This astonishing difference of over 600 degrees Celsius between day and night makes Mercury the planet with the most extreme temperature variations in our solar system. This stark contrast is a direct consequence of several key factors, primarily its lack of a substantial atmosphere, which plays a crucial role in regulating planetary temperatures on other worlds. On Earth, a thick atmosphere traps heat, acting like a blanket to prevent rapid temperature loss during the night. Greenhouse gases like carbon dioxide and water vapor absorb outgoing infrared radiation, re-radiating some of it back to the surface and keeping nighttime temperatures relatively mild. Mercury, however, possesses only an extremely tenuous exosphere, a wispy layer of atoms that are constantly being blasted off its surface by the solar wind and replenished from the planet itself. This exosphere is far too thin to retain any significant heat. Without an insulating atmosphere, the heat absorbed by Mercury's surface during its long day rapidly radiates back into space once the sun sets. The solid rock and dust of its surface are efficient at absorbing solar energy, but equally efficient at radiating it away without an atmospheric buffer. This rapid thermal emission leads to the precipitous drop in temperature, transforming the sun-baked landscape into an Arctic wasteland in a matter of hours. The thermal inertia of the surface is insufficient to mitigate this dramatic cooling. Mercury's slow rotation also contributes significantly to these extreme temperature differences. One full rotation on its axis relative to the stars takes approximately 58 Earth days. However, due to its eccentric orbit and orbital resonance, one solar day on Mercury, the time from one sunrise to the next, lasts about 176 Earth days. This means that any given spot on Mercury's surface endures an exceptionally long period of continuous daylight, followed by an equally long period of continuous darkness. During the prolonged daytime, the surface continually bakes under the relentless glare of the sun, accumulating vast amounts of heat. Conversely, during the extended night, the absence of solar input, combined with the lack of an atmosphere, allows the stored heat to dissipate unchecked into the vacuum of space for weeks on end. This extended exposure to both intense heating and subsequent deep cooling magnifies the temperature variations, creating an environment of extraordinary thermal extremes unlike any other planet in our immediate cosmic neighborhood. The extreme thermal stress from these massive temperature fluctuations has a significant impact on Mercury's surface geology. The repeated expansion and contraction of rocks and minerals can lead to thermal fatigue, potentially contributing to the fracturing and breakdown of surface materials over geological timescales. This process, known as thermal cycling, could play a role in shaping the regolith and contributing to the formation of smaller dust particles, though its overall significance compared to impact cratering is still being studied. The composition of Mercury's surface also influences how it responds to these temperature swings. The dark, rocky material effectively absorbs solar radiation, contributing to the high daytime temperatures. However, its emissive properties also allow for efficient radiation of heat at night. The absence of liquid water or a thick atmosphere to moderate these effects means that the surface directly bears the brunt of the solar furnace by day and the deep freeze by night, making it an exceptionally harsh environment. From a scientific perspective, these extreme temperature variations make Mercury an invaluable laboratory for studying planetary surface processes under conditions not found elsewhere. Understanding how materials behave and evolve under such severe thermal cycling provides critical data for refining models of planetary weathering and the physical properties of rocky bodies in airless environments. It also informs our understanding of how life, if it were to exist, would face unimaginable challenges on such a world. The discovery of water ice in permanently shadowed craters at Mercury's poles, as discussed in a later section, is even more remarkable when considering these extreme temperature fluctuations. The existence of ice, which requires consistently low temperatures, highlights the peculiar thermal dichotomy of the planet, scorching hot in direct sunlight, but consistently frigid in specific, perpetually shaded regions. This phenomenon underscores the complex interplay of orbital mechanics, topography, and solar radiation that defines Mercury's thermal landscape. Ultimately, Mercury's status as a planet of fire and ice is a testament to the diverse and often counterintuitive thermal environments that can exist in our solar system. Its lack of an atmosphere, slow rotation, and proximity to the sun combine to create a world where blistering heat gives way to bone-chilling cold with startling rapidity, challenging our preconceptions about what it means to be a hot planet and revealing the profound influence of atmospheric presence on planetary habitability and climate. Part 3. Strange Orbit and Einstein's Relativity. Mercury's orbit around the Sun is far from a perfect circle. It is highly elliptical, meaning its distance from the Sun varies considerably throughout its year. At its closest point, known as perihelion, Mercury is only about 46 million kilometers from the Sun. At its farthest point, or aphelion, it stretches out to approximately 70 million kilometers. This significant eccentricity, combined with its short orbital period of just 88 Earth days, makes Mercury a rapidly moving and dynamically complex celestial body, captivating astronomers for centuries. One of the most intriguing aspects of Mercury's peculiar orbit is the subtle yet persistent shift in its perihelion. Instead of tracing the exact same elliptical path around the Sun each time, the point of Mercury's closest approach to the Sun slowly rotates, or precesses, around the Sun over time. This phenomenon, known as the precession of the perihelion, was a major astronomical puzzle in the 19th century, as classical Newtonian mechanics could not fully account for its observed rate. Astronomers meticulously calculated all known gravitational influences on Mercury's orbit from other planets, particularly the massive Jupiter, which exerts a significant tug. These calculations successfully explained most of the observed precession. However, a small but persistent discrepancy remained. Mercury's perihelion was precessing by an extra 43 arcseconds per century that Newtonian gravity could not explain. This tiny, unexplained shift puzzled scientists and even led some to hypothesize the existence of an undiscovered planet, Vulcan, orbiting even closer to the Sun. The mystery of Mercury's anomalous perihelion precession remained unsolved for decades, until Albert Einstein revolutionized our understanding of gravity with his theory of general relativity in 1915. Einstein proposed that gravity is not merely a force, but a curvature in the fabric of space-time caused by the presence of mass and energy. Massive objects, like the Sun, warp the space-time around them, and planets follow these curves rather than being pulled by a force. According to general relativity, the Sun's immense mass creates a significant curvature in space-time that is most pronounced closest to it. As Mercury, being the innermost planet, orbits through this highly curved region, its path is subtly altered in a way that Newtonian gravity does not predict. The theory precisely accounted for the extra 43 arcseconds per century of precession in Mercury's orbit, fitting the observed data perfectly without the need for any hypothetical planet. This successful explanation of Mercury's perihelion precession was one of the earliest and most powerful confirmations of Einstein's general relativity. It demonstrated that for extreme gravitational environments, or for highly precise observations, Newton's laws of gravity, while incredibly accurate for most everyday phenomena, were an approximation of a deeper, more fundamental reality. Mercury's orbit became a pivotal test case, solidifying the revolutionary paradigm shift introduced by Einstein. The effect of general relativity on planetary orbits is most noticeable for Mercury, due to its extreme proximity to the Sun and its relatively fast orbital velocity. For planets further out like Earth or Mars, the curvature of spacetime is less pronounced at their orbital distances, and their slower speeds mean the relativistic effects are much smaller and harder to detect. Thus, Mercury serves as a unique cosmic laboratory for observing the subtle but profound consequences of a curved spacetime. Beyond the precession, Mercury's highly eccentric orbit also results in significant variations in solar flux, or the amount of solar energy it receives. At perihelion, Mercury receives about twice as much solar radiation as it does at aphelion. This dramatic change in energy input contributes to the extreme surface temperatures and influences the dynamic processes on the planet, including the liberation of atoms to form its tenuous exosphere. The interplay between Mercury's rotation and its highly elliptical orbit also creates a fascinating phenomenon known as a 3-to-2 spin-orbit resonance. For every 2 orbits Mercury completes around the Sun, it rotates exactly 3 times on its axis. This precise dance means that the Sun appears to do some very strange things in Mercury's sky. From some points on the surface, the Sun might appear to rise, set, and then partially rise again before continuing its path, or even halt and reverse direction briefly. This intricate dance between orbit and rotation ensures that every other time Mercury reaches perihelion, it presents a different face to the Sun, ensuring that over 2 Mercury years, all parts of the planet experience both the scorching day and the freezing night. This complex orbital choreography is a testament to the intricate gravitational dynamics at play in the solar system, making Mercury a prime object of study for celestial mechanics. The legacy of Mercury's strange orbit extends beyond a historical triumph for physics. It continues to be a subject of intense research, as scientists use precise measurements of its orbital parameters to test the limits of general relativity and search for even more subtle deviations that could hint at new physics beyond Einstein's theories. Missions like BepiColombo carry instruments designed to make such precise measurements, pushing the boundaries of our gravitational understanding. In summary, Mercury's unique and highly eccentric orbit, coupled with its close proximity to the Sun, makes it an unparalleled natural laboratory for exploring the profound implications of Einstein's general relativity. The resolution of the perihelion precession mystery stands as a monumental achievement in scientific history, fundamentally altering our perception of gravity and spacetime. Mercury truly embodies a celestial testament to the intricate and often counterintuitive laws governing our universe. Part 4. Surface scarred by craters and cliffs. Mercury's surface presents a stark and ancient landscape, heavily pockmarked by countless impact craters, bearing a striking resemblance to Earth's moon. This heavily cratered terrain is a direct consequence of billions of years of bombardment by asteroids and comets, remnants from the early chaotic solar system. Lacking a substantial atmosphere to burn up incoming projectiles, and without significant geological activity like plate tectonics to resurface its crust, Mercury retains a remarkably well-preserved record of these violent impacts. The craters on Mercury range dramatically in size, from tiny bowl-shaped depressions to enormous multi-ringed basins hundreds of kilometers in diameter. The largest and most prominent feature is the Caloris Basin, an immense impact structure approximately 1,550 kilometers across. This basin is so vast that it could almost encompass the entire country of India. The impact that created Caloris was so powerful that it sent seismic waves reverberating through the entire planet, leading to the formation of a chaotic, jumbled terrain on the exact opposite side of Mercury, appropriately named the Weird Terrain. Beyond the ubiquitous craters, Mercury's surface is also characterized by a unique and pervasive network of towering cliffs and scarps, known as roops. These magnificent geological features, some stretching for hundreds of kilometers and rising several kilometers high, are believed to be the result of the planet's global contraction. As Mercury's giant iron core gradually cooled and solidified over billions of years, the entire planet slowly shrank, causing its brittle crusts to wrinkle and fracture. This global shrinkage created tremendous compressional stresses, forcing sections of the crust to buckle and thrust upwards over adjacent sections, forming the distinctive lobate scarps. Observations from the Messenger spacecraft provided compelling evidence for this contraction, revealing fault lines and cliff faces that cut across craters, indicating that these shrinkage features formed after much of the heavy bombardment period. Scientists estimate that Mercury's radius has shrunk by approximately 7 kilometers due to this cooling and contraction. The presence of these contractional features, rather than extensive volcanic plains or spreading ocean basins seen on other planets, highlights Mercury's relatively static and ancient geological history. While some volcanic activity is evident in the smooth plains that fill certain impact basins, suggesting periods of molten material rising to the surface, the dominant forces shaping Mercury's crust appear to be impact events and global cooling rather than internal dynamism like Earth's plate tectonics. The composition of Mercury's surface, as revealed by spectral analysis from spacecraft, is primarily silicate rock, but with a surprisingly high abundance of volatile elements like sulfur and potassium, which were previously thought to have been largely baked out by its proximity to the Sun. This discovery challenges earlier models of Mercury's formation and suggests that the planet may have retained more of its original volatile rich material than anticipated, or perhaps acquired it later through impacts. The floor of many larger craters and basins on Mercury is often filled with relatively smooth plains, which are thought to be volcanic in origin. These plains indicate periods when lava flows erupted onto the surface, infilling the depressions created by large impacts. While not as extensive as the lunar Maria, these smooth plains show evidence of past volcanism, demonstrating that Mercury was not entirely geologically dead throughout its history, but its volcanic activity was likely less sustained and widespread than on Venus or Mars. Another intriguing feature observed on Mercury's surface is the presence of hollows. These are irregular, shallow depressions with bright, often bluish-white interiors, typically found on crater floors, central peaks, and basin rims. Scientists believe these hollows are formed by the rapid sublimation, or direct transition from solid to gas, of volatile rich material exposed to the intense solar radiation. This process could be actively ongoing, suggesting that Mercury's surface is still slowly evolving. The distribution and characteristics of these surface features provide an invaluable geological timeline for Mercury. The density of craters indicates the age of a particular region, with more heavily cratered areas being older. By studying the superposition of craters, scarps, and volcanic plains, planetary geologists can reconstruct the sequence of events that shaped Mercury's ancient and enduring landscape, offering insights into the early history of the inner solar system. Understanding Mercury's heavily scarred and contracted surface is crucial for comprehending the long-term evolution of terrestrial planets. It provides a stark contrast to Earth's dynamically recycled crust, showing what happens to a rocky world that has largely lacked significant internal heat for geological processes over billions of years. This ancient, preserved record makes Mercury a key object for studying the fundamental processes of planetary surface formation and modification in the absence of a thick atmosphere and active tectonics. In conclusion, Mercury's surface is a testament to cosmic violence and slow internal contraction. Its ancient, cratered face, interspersed with towering scarps, tells a story of relentless bombardment, followed by a gradual shrinking of the entire planet. This geological record, remarkably preserved due to the absence of active weathering and tectonic recycling, offers a unique window into the earliest, most tumultuous periods of our solar system's history and the fundamental processes that shape rocky worlds. Part 5. Water, Ice, and Polar Shadows. One of the most astonishing discoveries on Mercury, a planet scorched by the sun, is the definitive presence of water ice. This seemingly impossible feat occurs in the permanently shadowed regions within craters near its poles. Despite average daytime temperatures soaring to over 400 degrees Celsius, specific areas on Mercury's surface remain perpetually dark and incredibly cold, acting as natural cold traps where volatile compounds, including water ice, can persist for billions of years without sublimating. The existence of water ice on Mercury was first hypothesized in the early 1990s, when Earth-based radar observations detected highly reflective patches within polar craters. These radar bright spots were consistent with the presence of ice, which is an excellent reflector of radar waves. However, definitive confirmation required closer examination, as other materials could also produce similar radar signatures. The mystery lingered, fueling scientific curiosity about this unexpected possibility on such an intensely hot world. The breakthrough came with the NASA Messenger spacecraft, which orbited Mercury from 2011 to 2015. Messenger carried instruments specifically designed to investigate the polar regions. Its neutron spectrometer detected high concentrations of hydrogen in the permanently shadowed craters, a strong indicator of water ice. Hydrogen atoms, being lighter, are effectively slowed down by hydrogen and water molecules, creating a distinct signature that the spectrometer could detect, providing compelling evidence. Further confirmation arrived from Messenger's laser altimeter. By precisely measuring the reflectivity of the crater floors in these shadowed areas, the instrument observed distinct characteristics consistent with water ice. These areas showed a reflectivity pattern that matched laboratory measurements of pure water ice, further solidifying the evidence. In some cases, the ice appeared to be directly exposed on the surface, while in others, it was covered by a thin layer of darker, insulating material, possibly complex organic molecules or regolith. The mechanism by which water ice can survive on Mercury is due to the planet's minimal axial tilt, or obliquity. Mercury's spin axis is tilted by less than 1 degree relative to its orbital plane around the Sun. This extremely small tilt means that the Sun's rays always strike the polar regions at a very shallow angle. As a result, the bottoms of deep craters near the poles never receive direct sunlight. These areas are in perpetual shadow, creating extremely cold environments. Within these cold traps, temperatures can consistently hover around -173 degrees Celsius, well below the freezing point of water and cold enough to prevent ice from sublimating into space. Any water molecules, whether delivered by cometary impacts, asteroid impacts, or even outgassing from the planet's interior, that find their way into these shadowed regions become effectively frozen in time. Once trapped, the extremely low temperatures ensure their long-term preservation. The source of this water ice is a subject of ongoing research. The leading theory suggests that much of the ice was delivered by comets and water-rich asteroids that impacted Mercury over billions of years. These impacts would have deposited water molecules on the surface, and some of these molecules would have migrated as vapor across the planet until they condensed and froze in the permanently shadowed polar traps. Another possibility is that water could have formed from the interaction of solar wind protons with oxygen in Mercury's surface rocks. The discovery of water ice on Mercury has profound implications for our understanding of the distribution of water in the inner solar system and the potential for volatile delivery to terrestrial planets. It demonstrates that even the most extreme environments can harbor unexpected reservoirs of water, a critical ingredient for life. This challenges the notion that inner planets are completely desiccated, offering new perspectives on planetary habitability and the origins of Earth's own water. The estimated quantity of water ice in Mercury's polar craters is substantial, possibly totaling hundreds of billions of tons. If all the ice were melted, It could form a layer several meters deep across the entire floor of the cold traps. This significant amount makes Mercury an important target for future resource prospecting, especially if human missions eventually venture into the inner solar system, highlighting its potential utility beyond purely scientific interest. The presence of water ice also influences our understanding of Mercury's exosphere. As micrometeoroids impact the surface, they can kick up ice particles and water vapor into the exosphere. This continuous process contributes to the dynamic composition of Mercury's incredibly thin atmosphere, influencing chemical reactions and the interaction of the planet with the solar wind, providing another layer of complexity to this enigmatic world. In summary, the discovery of water ice in the permanently shadowed craters of Mercury's poles stands as one of the most remarkable findings in planetary science. It showcases the incredible extremes and surprising complexities that can exist even on the most inhospitable worlds. These frozen reservoirs of water not only challenge our preconceptions about planets closest to the Sun, but also offer tantalizing clues about the delivery of volatiles throughout the solar system, making Mercury an even more captivating subject of study. Part 6. The Messenger Mission and Discoveries. The Mercury surface, space environment, geochemistry, and ranging, or MESSENGER mission, was a groundbreaking NASA spacecraft that provided humanity with an unprecedented close-up view of Mercury. Launched in 2004, MESSENGER embarked on a challenging 7-year journey that included multiple flybys of Earth, Venus, and Mercury itself, before finally entering orbit around the innermost planet in March 2011. Its primary mission was to unravel the mysteries of Mercury's composition, geological history, magnetic field, and exosphere, fundamentally transforming our understanding of this enigmatic world. Prior to MESSENGER, our knowledge of Mercury was largely limited to brief flybys by the Mariner 10 probe in the mid-1970s, which only managed to image about 45% of the planet's surface. MESSENGER, however, became the first spacecraft to achieve sustained orbit around Mercury, allowing for comprehensive global mapping and detailed scientific observations over more than 4 years. This extended mission provided a continuous stream of data, painting a much richer and more complete picture of the planet. One of MESSENGER's most significant discoveries was the definitive confirmation of water ice and other volatile compounds in Mercury's permanently shadowed polar craters, as discussed in the previous section. Its neutron spectrometer and laser altimeter provided irrefutable evidence for these frozen reservoirs, shattering previous assumptions about the complete desiccation of planets so close to the Sun. This finding profoundly impacted our understanding of volatile distribution in the inner solar system. MESSENGER also revolutionized our understanding of Mercury's geological history. Its high-resolution cameras mapped the entire planet, revealing the pervasive network of lobate scarps or cliffs that crisscross its surface. These scarps provided direct evidence of Mercury's global contraction as its massive iron core cooled and solidified. The mission estimated that the planet's radius shrank by as much as 7 kilometers, a remarkable geological process unique in its scale among the inner planets. The spacecraft's X-ray spectrometer and gamma-ray spectrometer provided detailed elemental compositions of Mercury's surface. These instruments revealed a surprisingly high abundance of volatile elements like sulfur, chlorine, and potassium, as well as relatively low iron content in its crust compared to other terrestrial planets. This unexpected composition challenged prevailing theories of Mercury's formation, which predicted that such volatiles would have been largely lost due to its proximity to the Sun, suggesting a more complex accretion history. MESSENGER also extensively studied Mercury's surprisingly strong intrinsic magnetic field. While much weaker than Earth's, its presence indicated an active dynamo in its liquid outer core. The mission confirmed that the magnetic field is significantly offset from the planet's center and compressed on the day side by the solar wind, offering new insights into the dynamics of planetary magnetospheres and the properties of Mercury's internal structure. It also observed magnetic reconnection events, similar to those seen at Earth, affecting the exosphere. The mission also meticulously studied Mercury's ultra-thin exosphere, detecting and mapping the distribution of various elements like sodium, calcium, magnesium, and hydrogen. MESSENGER showed that this exosphere is highly dynamic, constantly being replenished by solar wind sputtering, micrometeoroid impacts, and volcanic outgassing, and then lost to space. This research helped scientists understand the interaction between Mercury's surface, its magnetic field, and the intense solar environment. MESSENGER provided invaluable data on Mercury's topography, allowing for the creation of precise global elevation maps. These maps revealed details about impact basins, volcanic plains, and the complex relief of its heavily cratered terrain. This topographical information is crucial for understanding the geological processes that have shaped the planet, from large-scale impacts to the subtle effects of thermal contraction. The mission concluded spectacularly in April 2015, when, after exhausting its fuel, MESSENGER was intentionally guided to impact Mercury's surface, creating a new crater and providing a final, dramatic data point. Its legacy is immense, fundamentally reshaping our understanding of the solar system's innermost planet and demonstrating the incredible resilience and ingenuity of robotic planetary exploration. In essence, the MESSENGER mission transformed Mercury from a dimly understood, largely unmapped world into a well-characterized planetary body. Its discoveries challenged long-held assumptions and provided a wealth of data that continues to be analyzed by scientists worldwide. It paved the way for future missions by highlighting new areas of scientific inquiry and demonstrating the challenges and rewards of exploring the solar system's innermost frontier. Part 7. BepiColombo and Future Exploration. Following the success of the MESSENGER mission, the European Space Agency and the Japan Aerospace Exploration Agency joined forces to launch an even more ambitious mission to Mercury, BepiColombo. Launched in October 2018, BepiColombo is a complex two-spacecraft mission designed to provide the most detailed study of Mercury to date, building upon MESSENGER's discoveries and exploring new scientific questions about this enigmatic planet. It represents a significant international collaboration in planetary science. The BepiColombo mission is composed of two independent orbiters: the Mercury Planetary Orbiter, or MPO, developed by ESA, and the Mercury Magnetospheric Orbiter, or MMO, developed by JAXA and renamed MEO. These two spacecraft are stacked together during their 7-year cruise to Mercury, which involves multiple gravity assist maneuvers around Earth, Venus, and Mercury itself. This intricate trajectory is necessary to slow the spacecraft down against the Sun's immense gravitational pull. Once BepiColombo arrives at Mercury in late 2025, the two orbiters will separate and enter their respective orbits. The MPO will focus on studying Mercury's surface and internal composition, with a suite of instruments designed to map its topography, analyze its elemental and mineralogical composition, investigate its interior structure, and study its exosphere. Its instruments include high-resolution cameras, spectrometers, a laser altimeter, and a radio science experiment. The MEO orbiter, on the other hand, is specifically designed to investigate Mercury's magnetic field and magnetosphere. Its instruments include magnetometers, plasma wave instruments, and particle detectors. MEO will study the interaction of Mercury's weak magnetic field with the solar wind, the dynamics of its magnetosphere, and the processes that generate its magnetic field within the planet's core. This dual orbiter approach allows for simultaneous, complementary observations of different aspects of the Mercury system. BepiColombo aims to address several key scientific objectives that MESSENGER could not fully resolve or to which it provided new insights. These include a more precise determination of Mercury's internal structure, particularly the state and size of its core. The mission also seeks to understand the origin of Mercury's magnetic field and how it interacts with the solar wind in greater detail. Furthermore, it will conduct a more thorough investigation of the planet's exosphere and the processes that create and sustain it. A significant goal of BepiColombo is to comprehensively map the distribution and composition of volatiles, including water ice, in Mercury's polar regions. With advanced spectrometers and higher resolution imaging, the mission will provide more detailed insights into the amount, purity, and geological context of these ice deposits, helping to refine theories about their origin and long-term preservation on the hot planet. BepiColombo also carries instruments to precisely measure Mercury's orbital parameters and its gravitational field. These measurements will allow scientists to conduct even more stringent tests of Einstein's general relativity in the strong gravitational field of the Sun, building upon the historical observations of Mercury's perihelion precession. Any tiny deviations from predictions could hint at new physics, pushing the boundaries of our understanding of gravity. Future exploration beyond BepiColombo might involve landers or even sample return missions. A lander could provide in situ analysis of Mercury's surface composition, search for deep ice deposits, and study seismic activity to probe the planet's interior directly. A sample return mission, while incredibly challenging due to the extreme conditions and high delta-V requirements, would allow for detailed laboratory analysis of Mercury rocks, providing unprecedented insights into its formation and evolution. Technological advancements, particularly in areas like high-temperature electronics, advanced propulsion, and autonomous navigation, will be crucial for these more ambitious future missions. Exploring Mercury is inherently difficult due to the intense solar radiation, the planet's strong gravity well, and the extreme thermal environment, all of which pose significant engineering challenges for spacecraft design and operation. In conclusion, BepiColombo represents the cutting edge of Mercury exploration, promising to unlock even more secrets of this fascinating planet. Its dual orbiter design and advanced instrumentation are poised to deliver a wealth of new data, furthering our understanding of Mercury's internal structure, magnetic field, exosphere, and surface composition. The mission also sets the stage for even more ambitious future endeavors, demonstrating humanity's enduring quest to explore and comprehend the innermost reaches of our solar system. Part 8. Mercury in Mythology and Astrology. Long before it was understood as a scorching hot, cratered world, Mercury held a significant place in the myths and astrological beliefs of ancient civilizations. Due to its rapid movement across the sky, completing its orbit in just 88 Earth days, it was naturally associated with swiftness and communication. Its elusive nature, always appearing close to the sun as either a morning or evening star, further added to its mystique and contributed to its varied interpretations across different cultures. In Roman mythology, the planet was named after Mercury, the winged messenger of the gods. He was known for his speed, agility, and ability to travel swiftly between the mortal and divine realms. As the god of trade, eloquence, messages, travelers, and thieves, Mercury's attributes perfectly aligned with the fast-moving celestial body. The Romans also equated him with the Greek god Hermes, who also served as a messenger and patron of many similar domains. This strong mythological association has endured, influencing the planet's cultural perception even today. The Greeks, preceding the Romans, knew the planet by two names, Apollo when it appeared as a morning star, and Hermes when it was an evening star. This dual identity reflected its rapid shifts between being visible before dawn and after dusk. Eventually, they recognized these as the same celestial body, and settled on Hermes, acknowledging his role as the swift, cunning, and intelligent deity. This early recognition of its rapid motion underscored its significance in their cosmological observations. In ancient Babylonian astronomy, Mercury was associated with Nabu, the god of wisdom, writing, and scribes. His swiftness was linked to the rapid transmission of knowledge and decrees. The Babylonians were keen observers of planetary movements, and Mercury's quick dance across the sky made it a celestial harbington of change and intellectual pursuits, further tying it to the realms of communication and intellect, which are common themes across cultures. In traditional Western astrology, Mercury is considered the ruling planet of communication, intellect, logic, reasoning, and travel. Astrologers believe that the position of Mercury at the time of an individual's birth influences their communication style, thought processes, and how they express themselves. It is said to govern areas such as writing, speaking, learning, and negotiations, emphasizing its role as a celestial embodiment of mental agility and the exchange of information. The phenomenon of Mercury retrograde is a well-known concept in astrology, where, due to an optical illusion caused by the relative speeds of Earth and Mercury in their orbits, Mercury appears to move backward in the sky. Astrologically, this period is often associated with disruptions in communication, technological glitches, travel delays, and misunderstandings. It is viewed as a time for reflection, reevaluation, and caution, rather than initiating new projects, highlighting the planet's perceived influence on daily life. In Hindu astrology, or Jyotish, Mercury is known as Buddha, representing intellect, communication, and commerce. Buddha is associated with sharpness of mind, analytical ability, and adaptability. Individuals with a strong Buddha in their birth chart are believed to possess excellent communication skills, business acumen, and a keen intellect. Its swift motion is also linked to quick decisions and a fast-paced mental life, echoing the Roman and Greek interpretations. Across various cultures, Mercury's association with messengers, communication, and intellect highlights a shared human observation of its rapid celestial dance. Its elusive appearances and quick transit across the heavens naturally led ancient peoples to imbue it with qualities of speed, intelligence, and the transmission of information, connecting the cosmic with the human experience in profound ways. These ancient interpretations, while not scientific, reflect early attempts to understand and categorize the cosmos, linking celestial phenomena to human characteristics and events. They provide a rich cultural context for our modern scientific exploration of Mercury, showing how humanity has always sought meaning and connection with the celestial bodies orbiting our Sun, influencing language and symbolic thought for millennia. In essence, Mercury, the planet, has long served as a powerful symbol in mythology and astrology, embodying speed, communication, and intellect across diverse cultures. From the swift messenger gods of Rome and Greece to the patron of wisdom in Babylon and the ruler of communication in modern astrology, its rapid movement and elusive nature have consistently inspired rich narratives and beliefs. These ancient associations provide a fascinating backdrop to our contemporary scientific endeavors to understand this dynamic and perplexing world. Part 9. Why Mercury is so hard to visit. Visiting Mercury presents an extraordinary challenge for space engineers and mission planners, often described as one of the most difficult feats in robotic space exploration. While its proximity to Earth might suggest an easier journey compared to outer planets, the reality is that reaching and orbiting Mercury requires overcoming a unique combination of formidable obstacles, pushing the limits of spacecraft technology and propulsion. These difficulties stem primarily from the Sun's immense gravitational pull and the intense solar radiation. The first major hurdle is the sheer amount of energy required to simply reach Mercury. To travel to an inner planet, a spacecraft must essentially fall deeper into the Sun's gravity well. This means it needs to shed a tremendous amount of orbital energy relative to Earth. Paradoxically, it requires more fuel to slow down and fall towards the Sun than it does to speed up and travel outwards to planets like Jupiter or Saturn. This deceleration is a costly process in terms of propellant. Instead of merely coasting, a spacecraft bound for Mercury must perform numerous gravity assist maneuvers, often involving flybys of Earth, Venus, and Mercury itself. These flybys are carefully choreographed to use the gravitational tug of these planets to gradually slow the spacecraft down and adjust its trajectory, allowing it to eventually match Mercury's orbital velocity and enter orbit. Such trajectories are complex, time-consuming, and require extreme precision and navigation, extending missions over many years. Once near Mercury, the spacecraft faces the challenge of entering orbit around a relatively small planet while still under the dominant influence of the Sun's gravity. This requires a significant final burn of its thrusters, consuming a large fraction of the remaining propellant. The high delta V, or change in velocity, needed for orbital insertion around Mercury is among the highest for any planetary mission, emphasizing the immense engineering effort involved. The intense solar radiation near Mercury poses another critical challenge. At Mercury's orbital distance, the Sun's radiation is approximately 11 times more intense than it is at Earth. This extreme solar flux would quickly overheat and damage conventional spacecraft. Consequently, missions to Mercury require sophisticated thermal control systems, including robust multi-layered insulation, highly reflective coatings, and massive ceramic sunshields, like the one employed by Messenger, to protect sensitive instruments and electronics. The severe thermal environment also results in extreme temperature gradients across the spacecraft. The side facing the Sun might experience temperatures exceeding 350 degrees Celsius, while the shadowed side plunges to hundreds of degrees below zero. Designing components that can withstand such a vast range of temperatures and rapid thermal cycling is a significant engineering challenge, requiring materials science at its absolute best to prevent cracking, degradation, or operational failure. Communication with spacecraft at Mercury is also more difficult than with missions further out in the solar system. The Sun, positioned between Earth and Mercury for significant periods, can interfere with radio signals. Additionally, the vast distances, though shorter than to outer planets, still mean that powerful antennas and sophisticated communication protocols are necessary to transmit data back to Earth reliably, especially when the spacecraft is at its farthest point from Earth. The scientific instruments themselves must also be designed to operate under these extreme conditions. Detectors, cameras, and spectrometers need to be robust enough to function reliably in high temperatures and under constant solar bombardment. This often means using specialized materials, passive cooling systems, and innovative instrument designs that can collect high-quality data without being compromised by the harsh environment. Finally, the relatively small size of Mercury means its gravitational field is weaker than that of Earth or even Mars, making orbital mechanics more sensitive to perturbations and requiring precise thruster firings to maintain stable orbits over long periods. Fuel conservation becomes paramount, as every maneuver depletes the limited propellant carried on board, ultimately determining the lifespan of the mission. In summary, visiting Mercury is an extraordinary feat of engineering, demanding unprecedented levels of thermal protection, complex trajectory planning, and massive propulsion capabilities. The intense solar radiation, the deep gravity well of the Sun, and the planet's own gravitational challenges combine to make Mercury one of the most inhospitable and technically demanding destinations in our solar system, a testament to the ingenuity required for planetary exploration. Part 10. What Mercury teaches us about planet formation. Mercury, despite its harsh environment and diminutive size, serves as an invaluable natural laboratory for understanding the fundamental processes of planet formation, particularly in the inner regions of stellar systems. Its unique characteristics, from its giant iron core to its anomalous composition and ancient, preserved surface, challenge existing models and provide critical data points that help scientists refine their theories about how rocky planets coalesce and evolve under extreme conditions. The most striking feature of Mercury, its disproportionately large metallic core, provides crucial insights into early solar system dynamics. Conventional planet formation models suggest that planets accrete material from the protoplanetary disk, with heavier elements sinking to the core and lighter silicates forming the mantle and crust. Mercury's immense core-to-mantle ratio suggests either an atypical accretion process in the intensely hot inner solar nebula, where lighter materials might have been boiled away, or a catastrophic event. The leading theory involving a giant impact, where an early, larger Mercury was stripped of most of its silicate mantle by a massive collision, has significant implications for understanding the prevalence of such events in the chaotic early solar system. If proven, it demonstrates that violent impacts were not just localized phenomena, but potentially major drivers of planetary evolution, capable of fundamentally altering a planet's composition and structure. This informs models of Earth's moon formation and similar events on other worlds. Mercury's surprisingly high abundance of volatile elements like sulfur and potassium, observed by MESSENGER, challenged earlier models that predicted these elements would have been largely vaporized by the sun's heat during formation. This discovery suggests that either Mercury formed from material that was not as thoroughly baked out as once thought, or that volatiles were delivered to the planet later through impacts with comets and asteroids from the outer solar system. This challenges the simplicity of early solar system chemical gradients. The planet's ancient, heavily cratered surface, largely preserved due to the absence of significant geological activity or a thick atmosphere, provides a unique geological timeline. It offers a direct record of the intense bombardment period that characterized the early solar system, a phase critical for understanding how inner planets accrued their mass. By studying the size and distribution of craters, scientists can infer the flux of impactors over billions of years, providing context for the impact histories of Earth, the Moon, and Mars. The global contraction evidenced by Mercury's pervasive lobate scarps demonstrates a fundamental process of planetary cooling and shrinkage that can occur in rocky bodies. This geological phenomenon is a stark contrast to Earth's active plate tectonics, showing the diverse pathways of planetary evolution based on internal heat budgets and composition. It helps scientists understand how planets cool down and how their crusts respond to these internal changes over vast geological timescales. The presence of water ice in permanently shadowed polar craters, combined with the presence of volatiles in the surface composition, suggests that water and other crucial compounds can survive and even be preserved in the most extreme environments. This finding has broad implications for the distribution of water in the solar system, hinting that water might be more common on airless bodies, even in the inner solar system, than previously imagined, which has consequences for the origins of life and future resource utilization. Studying Mercury's weak but active magnetic field also sheds light on the conditions necessary for generating a planetary dynamo. Its unique core composition and thermal history provide constraints on how internal heat flows, and how molten metal convects to create a magnetic field in a relatively small planet. This data helps to refine models of planetary interiors and the processes that govern the generation and evolution of magnetospheres across the solar system. Moreover, the precise measurements of Mercury's orbit and its perihelion precession provide a continuous, high-fidelity testbed for Einstein's theory of general relativity. This confirms that for objects close to a massive star, the curvature of spacetime significantly influences orbital mechanics, offering profound insights into the fundamental nature of gravity and the structure of our universe. It demonstrates how planetary observations can validate cutting-edge physics. In essence, Mercury acts as a crucible of planetary formation, showcasing the extreme conditions under which rocky worlds can form and evolve near a star. Its anomalies and unique characteristics force scientists to reconsider their assumptions, expand their models, and ultimately gain a deeper, more nuanced understanding of the diverse processes that shape planets throughout our solar system and beyond. Every discovery on Mercury is a clue in the grand puzzle of cosmic creation.